Hi everyone, and welcome to another video of the SAFI webinar series. In this video, we are going to have an overview of cables. To add a cable to the model, we need to create a cable section. To define a cable section, the user needs to specify the cross area and the nominal diameter and assign a material. The material properties will be used to calculate the breaking strength of the cable. A cable has no bending, shear, compression, or torsion stiffness. Thus, all releases at the ends of the cable members are ignored and considered as tension-only members. After creating a cable section, the user needs to assign the cable section to a member by editing the member attributes. When the cable section is assigned to a member, the user can edit the cable parameters. The cable parameters allow the user to specify what type of cable it is. For example, is it a linear cable or a catenary nonlinear cable? For each type of cable, the user needs to specify the different parameters, including pretension, undeformed length, and tension at the ends of the cable and the sag. The first type of cable we have is a linear cable. To define a linear cable, the user must specify the initial stress, Pi, in the cable before any distortion in the model. The linear cable element may be used in a linear analysis, P-delta analysis, buckling analysis, and moving load analysis. It is important to enable the one-way element option when we run the analysis if we have cables in the model. The second type of cable is a catenary cable. The catenary cable is a highly nonlinear element used to model the catenary behavior of cables suspended between 2 points and it's subjected to its own weight. The formulation accounts for the large deformations of nonlinearity. The stiffness of the catenary element is a function of the cross-section area, the elastic modulus, the initial length, the transverse load, and the position of the joints. The nonlinear analysis is required for this type of element to accurately model the behavior of a catenary cable. For other analysis types allowed in SAFI, the results are approximate. The stiffness of the cable for this type of analysis is computed based on the undeformed initial state of the cable. Moreover, the stiffness of the catenary elements are computed using only the self-weight of the cable for linear analyses without any iteration, as well as other analyses including buckling, frequencies, seismic or dynamic, and moving load analyses. When a cable is not subjected to any loading, the minimum self-weight is assumed, which allows using the equations of the catenary cable. However, it is always recommended to apply a self-weight load for each load combination. Let's start our demo. To find the cables section, we go to the menu Tables, then Sections, and we select Cables. We can also access this command by using the Sections toolbar. To display the Sections toolbar, we do a right-click on the mouse here and we select Sections. The Cable Section command is available by clicking on this button. To add a cable section, we click on the button Add a new tab. From this list, the user can create a custom cable or select a cable from the libraries provided by the software, including the American ASTM library and the Canadian library. To create a custom cable, we select the first option in the list. First, we need to assign a material to the cable. If the material is not available in the model, we can click on this button to access the Materials command, and the user can create a material from this dialog box. Next, we need to specify the diameter of the effective area of the cable. So, when we specify these parameters, the effective area will be used to calculate the nominal breaking strength and the self-weight. The diameter of the cable will be used to calculate the different type of loads, including the wind load and the ice load. The last step is to assign a name to the cable. We can do that by double-clicking on the tab or clicking on the button Rename Current Tab. We then click OK to validate. Now let's add a member to this model. To assign the cable section to the member, we need to edit the attributes of the member. We can edit the attributes of the member by double-clicking on the member or using the command Edit Member. If we are editing a selection of members, we can use the command Member Attributes on the Addition toolbar. When we select the cable section from this list, the user can edit the cable parameters using this button. In the Cable Parameters dialog box, the user can specify the type of cable. So, we have linear cables and catenary cables. For linear cable types, the user needs to specify an initial strength. For linear cable types, the user needs to specify an initial stress. For example, 20,000. We click OK to validate, and then we click OK again. Now we can see on screen the color of this member changed. It's displayed as a green discontinuous line. A green discontinuous line means that this member is in tension only. All the type of cables behave as a tension only members. Let's open an example of linear cables. In this example, we have a column attached to two cables at the top. If we edit the attributes of these cables, we see that we applied an initial stress of 50,000 psi. For the loading, we have two load combinations. So, the first load combination includes only the self-weight. The second load combination includes the self-weight and a horizontal force at the top of the column. Let's run the analysis. It is important to enable one-way elements by checking this box. For this specific example, we want to display the internal stresses. By default, the software doesn't calculate the internal stresses. To have access to this result, the user needs to check these boxes when we run the analysis. For the graphical results, we'll check the internal deformations and the axial stress, Sx. We notice that the column is under compression and the axial stress in the cables are less than the initial stress. Now let's look at the second load combination. For this load combination, we see that the cable on the right has a red square with an X on it, which means that this cable has been deactivated. Linear cables will be deactivated if they are under compression. In this case, the cable has no effect on the analysis results. If we do a copy of this model, excluding this cable, we should obtain the same results. Let's use the command copy, and I'm going to copy this model here. Let's put 900 inches. The model on the right-hand side and the model on the left-hand side for this load combination are equivalent. If I run the analysis again, we can see that the results are the same. Let's open another example of a catenary cable. To define a catenary cable, in the cable parameters, the user needs to specify the type of cable as catenary nonlinear. Catenary cables require nonlinear analysis. To calculate the position of the cable joint and the tension at the joints, the user can specify a calculation method. One of the important parameters that we need to calculate is the undeformed length of the cable. The undeformed length, L0, is displayed on the image here. To calculate the undeformed length, there are many methods that are available for the user. The first one is to specify the undeformed length. If we know the undeformed length, we can specify it in this box. For example, on the right-hand side, we have a dynamic preview of the parameters that we specified on the left-hand side here. The second option is to specify a ratio of the undeformed relative length L0 divided by LC. LC is the distance between the joints. I and J are the joints of the cable. In many cases, we don't know the undeformed length, but we know the tension at the end of I or J of the cable. So in this case, we can specify the tension instead. For example, if I specify a tension of 4 kips, we can see a preview of the deformation of the catenary cable. The next option is the horizontal tension component TH. If we know this value, we can specify it as well. The next option, low points vertical sag. For this option, the user needs to specify the vertical sag or the lowest point of the cable. For example, 1 foot. The next option is the maximum vertical sag or Smax. Smax is defined here in this image. The last option, the user doesn't need to specify anything and it corresponds to the minimum tension possible at the ends of the cable. The program will display the cord length, LC, which is the distance between the joint I and J, and also the self-weight. Now, in this example, we have a catenary cable suspended at these two joints and we have two load combinations. The first one, which is a dead load. The dead load, in this case, is applied as a uniform load. So, 3.16 pounds per foot is the dead load. The next load combination, we add a concentrated load at this specific joint. The only type of loads that we can apply on a cable member is a uniform load or a thermal load. If we want to apply a concentrated load, the only way to do it is to add a joint, or we can add a joint by subdividing the cable using the command subdivide members in plate, and then we can apply a concentrated load on that specific joint. Let's run the analysis. Catenary cables are nonlinear cables, so we need to run a nonlinear analysis. If we use any other type of analyses, the program will display a warning message if we click yes when we run the analysis, even if the results are not accurate. If we say no, the analysis will be aborted. For this example, we run a nonlinear analysis. Now to display the results. First, let's display the load combination, which is a dead load only. We can see that the deformation of these joints are almost zero because the only load that we apply to this specific cable is the dead load or the self-weight. The undeformed length that we used for this cable corresponds exactly to the self-weight of this cable. The second load combination includes the dead load and the concentrated load. For the second load combination, we can see that both cables are in tension because the concentrated load that we added at this specific joint. For the second load combination, we can see that both cables are in tension because of the concentrated load that we added at this specific joint. That's it for this video. Thank you for watching and catch you in another one of our webinar series videos.